Hello everyone, in this talk, I'll present our paper on risk-aware temporal cascade reconstruction to detect asymptomatic cases. My name is Hankyu. I'm a PhD student in computer science at the University of Iowa. This is a collaborative work, and the work was funded by CDC Mind Healthcare Network and NSF. So with this, I'll start my presentation. For many infections, asymptomatic cases present a major obstacle to precisely understand how the infection is spread. For instance, in infectious diseases such as COVID-19 and CDI, so CDI is a common healthcare-associated infection, asymptomatic cases play a significant role in the disease spread. So there's a need to detect asymptomatic cases. However, often we don't have ground truth data on asymptomatic cases because they don't get tested. Therefore, we need a method to detect them and to evaluate them. Often, missing infections problem is solved using directed standard tree problem. So what is directed standard tree? It takes an input as a directed graph with edges have weights on it, and there's a special vertex R, which is root, and a set of special vertices S that are called terminals. And the goal is to find the tree rooted at R, spans to all the terminals such that it minimizes the cost of the tree, where the cost is defined as the summation of the edge weights in the tree. We can model missing infection using DST by the following. We use the contact network. We set infection source as the root, observe the infections as terminals, likelihood of transmission as edge weights. Then the output tree from the DST serves as an infection cascade. And also, the intermediate nodes in the solution can be interpreted as missing infections. There are many papers that uses DST to infer missing infections. However, the limitation is that individual susceptibility is ignored. So this is an important aspect in the disease spread. So can you take this into account? So can you take into account both the disease flow and the individual risk? More specifically, if we have a prior knowledge of the likelihood of each node being colonized, can DST use this information? And the answer is yes, and we propose to use directed price collecting standard tree to solve this problem. So everything else is very similar to DST, except that it has an additional input such that all the nodes has a node weight. And also there is a change in the cost function of the tree, cost of the tree, where we have this term which corresponds to the summation of the node weights that are excluded from the tree. So this objective function of the directed PCST aims to balance two weights. A weight due to the edges included in the tree, and another set of weights that are from the nodes that are excluded from the tree. So therefore, the optimal solution tree uses a combination of low weight edges and high weight nodes. And we can use the likelihood of node being an asymptomatic as the weight of the nodes in the graph. Okay, so now let's look at the formal problem definition. So we have asymptomatic case detection that we are given a temporal network and a sequence of observed cases, and the goal is to find asymptomatic cases over time. We propose to solve this using directed PCST, as we discussed in the previous slides. So now I'll discuss how we prepare the input for the directed PCST and how we solve the directed PCST. This is our overall solution. So we start from the hospital operations database. Then we pre-process the inputs for the directed PCST, and we solve it to get asymptomatic cases. Then we evaluate the asymptomatic cases in both synthetic data experiment and the real data experiments. And I'll explain each of these components in detail in the later slides. So first of all, we need to compute the individual risk. And this is challenging because the data lacks ground truth labels for asymptomatic carriage. So we need to make hypotheses to enable the model training. And in other words, with these two hypotheses, we can train a binary classifier for predicting symptomatic CDI cases using standard features for this task. So after training, we use the output probability of the instances that are patients as the asymptomatic likelihood. Then we construct a temporal network where the temporal network is daily snapshots of patient visits in the hospital. So each node is a patient visit. Each node has an indicator on whether it's a CDI case or not, and also likelihood of being an asymptomatic, which is computed from the previous step. And there are edges which denote whether the two patients visited the same unit in the hospital in the day or not. Then from this temporal network, we construct a time-expanded network. And we do this by adding a dummy node. We connect this dummy node to all the nodes in the graph. And also we add cross edges for context between patients. In the time-expanded network, terminals represent observed cases, and node weights represent the asymptomatic likelihood. And notice that this time-expanded network is a directed acyclic graph, DAG, and this plays an important role later on. And also note that we parameterized the edges with gamma and beta, and later we explore the space of these parameters in the experiments. So now we have all the inputs that are needed for the directed PCST. So let's solve it. I'd like to emphasize that directed PCST is computationally very challenging, even to approximate. Therefore, we reduce the directed PCST to directed standard tree to obtain scalable algorithms. And we do this by, from the time-expanded network, we create a graph with only edge weights. And how we do this is that for each edge, if the target node of that edge is a non-terminal node, then we subtract a scaled node weight of this terminal node from the edge weight. And we also show that the optimal directed standard tree in the new graph is in fact the optimal directed, the optimal directed price correcting standard tree in the original graph. And we also show that the approximation factor is preserved in this reduction. We propose 3 approximation algorithms to solve DST on this new graph that are greedy algorithm, linear programming, and minimum cost algorithms. Please see the details of these approximation algorithms in the paper. And each of these algorithms returns a solution tree, and we interpret the nodes in the paths from the root to the terminals as asymptomatic cases. Okay, now the experiments. So since this is the first work on detecting asymptomatic cases in a temporal network that takes individual risks into account, there are no directly comparable methods. However, we compare the performance of our approach against the following natural baselines that are frontier contact top K, length of stay top K, and the state-of-the-art approach, which is called for a closely related task. And now we show the performance of the method in the synthetic data. And I'd like to note that the point of using synthetic data is that it provides us a ground truth on asymptomatic cases. So for this experiment, we use the data of 1 month of patient data to generate time-expanded network. We run simulations from multiple sources to obtain a set of observed symptomatic cases and a set of asymptomatic cases. And then we measure the success based on the overlap of inferred asymptomatic cases and the ground truth asymptomatic cases. And the result is shown in these figures. And as you can see in both of these two evaluation metrics, our method, which is in blue, outperform over the other baselines. And from this result, we can claim that our method finds the right balance between the likelihood of node being exposed to the disease via edge weights and the likelihood of nodes developing symptoms via node weights. Now, finally, we apply our method for asymptomatic case detection to the important task of predicting symptomatic CDI cases on actual hospital data. We train a neural network with two types of features that are standard features for CDI and asymptomatic pressures. These asymptomatic pressures are a set of features that measures the exposure to the newly identified asymptomatic CDI cases. And I'd like to note that asymptomatic pressures are generated from the solutions from our approaches and the baselines. And we use 3 months of data and investigate if adding asymptomatic pressures improves the performance of the task. So here, this is the result in AUC scores. This horizontal dashed line corresponds to a baseline that do not use asymptomatic pressures as features. And our method is in blue. And the key observations from this result is that our method outperforms all the baselines. And by adding asymptomatic pressures from our method, improves the symptomatic cases prediction task. So with this, I'd like to end my presentation, and thank you.